Okay, polynomial inequalities, 3.6 again. Definition of polynomial inequality. Let f of x be a polynomial, then an inequality of the form f of x is less than 0, f of x is greater than 0, f of x is less than or equal to 0, or f of x is greater than or equal to 0 is called a polynomial inequality. All right, so if we want to write the solution set for a polynomial inequality, so for part A, we have x squared minus 6x plus 5 is greater than 0. So what we mean by find the solution set is we're looking for all values on the x-axis where f of x, meaning y, is greater than 0. That means positive. That means above the x-axis. So if you look at that, you can see that the places where it is above the x-axis are the areas from negative infinity up to 1, not including 1, and from 5 to infinity. So that is the solution set for that inequality. That is where the function is greater than 0. So for part B, it's less than or equal to 0, same function. And what we're looking for is the solution set is the set of all values on the x-axis where f of x, meaning y, is less than or equal to 0. That means negative or 0. That means below or on the x-axis. And so this is where that happens. And so between 1 and 5, including 1 and 5, is going to be the solution set. So that is what we mean by solving a inequality, a polynomial inequality. So here's another example. Solve the quadratic inequality 3x times x minus 1 is greater than 10 minus 2x. So the first thing we have to do is write the inequality in the form f of x is greater than 0. We want to get everything on one side. So we can do that. I'm just going to click through this real quick because you can pause it if you need to write this down. And so we're getting it all on one side. And now we're going to find the real zeros of the related equation f of x equals 0. So we've got 3x squared minus x minus 10 is equal to 0. And so we just need to factor that. We'll have 3x plus 5 times x minus 2, which means that the solutions are negative 5/3 and x equals 2. So what we're going to do is we're going to break up the x-axis into intervals defined by those boundary points. And so we're going to have negative infinity up to negative 5/3, then negative 5/3 to 2, and then 2 to positive infinity. And we're going to set up, we're going to look at the x-axis and just mark those two zeros. And we're going to make a chart where we look at what's happening to each factor on those intervals. So for the interval from negative infinity to negative 5/3, we can just try one of the values that's in that interval for x. So negative 2, if we try that, we get 3 times negative 2 plus 5, which is negative 1. So the function right there, that part of the function, that factor is negative. Next, we can try that same negative 2 in the second factor, which is x minus 2, and we get negative 4. So that makes that factor negative. So 3x plus 5 times x minus 2, negative times negative is positive. So the function is positive on that interval. Now we're going to look at the interval from negative 5/3 to 2. So we're going to try an x value in that range. So that could be 0, the easiest one. You plug that into 3x plus 5, and you get 5. So that means that factor is positive on that interval. Next, the factor x minus 2, if you put 0 in there, you get negative 2. So the factor is negative on that interval. So when you multiply the two factors together, positive times negative is going to give you negative. So on that interval, the function is negative. From 2 to infinity, we could try 3. Plug that into 3x plus 5 and you get 14. That's positive. For the x minus 2, that's 3 minus 2 is 1. That's also positive. And so the function is positive on that interval. And so you can see where the function is greater than 0, which is what we're looking for. It is a strict inequality, so we're looking greater than 0, and that happens on this interval and this interval. That's when the function is positive. So those two sets, negative infinity up to negative 5/3, union 2 to infinity, that's going to be your solution set because you can see that is where the function is above the x-axis. Those values of x from there down, and from there up, those are the places on the x-axis. Those are the solutions, the x values where this function is positive above the above the x-axis. And you can see that, on the graph. If you had the graph already, you'd be able to see it immediately, but we're just talking about how to figure this out if you don't have the graph. Here's another example that's a little more complicated, and it'll help you see why we're doing all this work. I mean, on the one before, you might not have needed to do all that, but as the graphs get more complicated, you kind of do because there's just a lot more going on. So solve the inequality x to the fourth minus 12x is greater than or equal to 8x squared minus x cubed. So again, the first thing we're going to do is write the inequality in the form f of x is greater than 0. So we're going to get everything on one side, and this is what it looks like. And now we are going to find the real solutions to the related equation f of x equals 0. And we can factor out the x, but we also have to solve that cubic polynomial. And so to do that, you might have to go through a few values. Remember that the possibilities are going to be all the factors of 12. And so I did that already, and I found out that -2 works. So I just put that in for synthetic division, do that synthetic division out, and you're going to get that your polynomial that's left over is x squared minus x minus 6. So the factorization is going to be x times x plus 2, because -2 is a 0, and then you've got that quadratic left over, which is factorable, so you'll have x plus 2 times x plus 2 times x minus 3. So that's the factorization of this polynomial, and it looks like this. So you can see what the solutions are for what the zeros of the polynomial are. That's going to be 0, -2, and 3. So the intervals that you're going to set up are going to be on your x-axis. You're going to be going from negative infinity up to -2, from -2 to 0, from 0 to 3, and from 3 to infinity. So you're going to set up your little table, and you're going to have these intervals that you're going to look at for each factor. All right, so these are pretty simple. We don't necessarily have to plug in anything because we can see it super fast what's going to happen. So the sign of x in each interval, all right, in the first interval, x is going to be negative infinity to -2. -2 to 0, again, x is negative in that interval. From 0 to 3, x is positive. From 3 to infinity, x is positive. Then the sign of x minus 3, you can see that from negative infinity up to -2, all those x values are going to make that negative. From -2 to 0, again, you're going to have -2 minus 3, and then everything between is still going to make it negative. For x minus 3 between 0 and 3, again, it's going to be negative because x is less than 3, so that's going to come out negative. And then 3 to infinity is the only time when that x minus 3 factor is going to be positive. X plus 2 squared is always positive because it's a square. So when you square something, it becomes positive. All right, so here are the signs for all the factors, and this will tell you what the sign of the function is over each of these intervals. So over the interval from negative infinity to -2, you've got a negative times a positive makes positive. From -2 to 0, you've got negative, positive. Again, that makes positive. From 0 to 3, you've got positive, negative. That's going to be negative. And then from 3 to infinity, they're all positive, so that's going to be positive. So the places where this function is positive are from negative infinity all the way up to 0. And since this is it's greater than or equal to 0, are the things we're looking for, we can include 0. and we can include -2. So we can say that all the way from -infinity up to 0, the function stays positive. And you can see that in the graph right here. It's above the x-axis the whole time from -infinity all the way up to 0. So that interval, -infinity up to 0, and we can include 0 because it's greater than or equal to 0. And then the other interval where it is positive is going to be 3 to infinity, and we're going to include 3 because it's allowed to equal 0. And so this would be the solution set for this polynomial inequality. Okay, so there are going to be some problems where you can easily find the signs of the polynomial at different places without even having to really do much work at all. So there might be a few problems like this in your homework where they're kind of checking to see if you might notice. So this is a perfect square trinomial. It's 2x minus 3 quantity squared. If you happened to notice that, you'd be able to answer these really quickly. Because for part A, it says, when is that polynomial less than 0? It's never less than 0. So it's always positive because it's a perfect square. On part B, when is it less than or equal to 0? Well, it's never less than 0. We just stated that. But it does equal 0 when x is equal to 3 halves. So the solution set for that would just be 3 halves. For part C, when is it greater than 0? Well, it's always greater than 0 except when it equals 0, which is at 3 halves. So for this one, you would say -infinity up to 3 halves union 3 halves to infinity. And then part D, when is it greater than or equal to 0? And that is everywhere. So that would just be -infinity to positive infinity. Okay, we're going to talk about rational inequalities now. We have the picture here, the graph of the function 2x minus 5 over x plus 2. And you can look at the graph to see what's going on in these different places. So 2x minus 5 over x plus 2 is less than 0. That only happens this part of the graph, where it's below the x-axis, and that happens as x. So there's an asymptote at x equals -2. So from -2 up to the 0 of the function, which is at 5 halves. So that would be the solution set for that one. We're not including 0. So the solution set for that would be from -2 up to 5 halves, not including 5 halves. For 2x minus 5 is greater than 2x minus 5 over x plus 2 is greater than 0. You can see that that happens on the left side of the asymptote. So from -infinity up to -2, but not including -2 because the asymptote is not something that the graph will ever touch. And then it's also positive from 5 halves up to infinity, but not including 5 halves because we don't want it to equal 0. And then 2x minus 5 over x plus 2 is less than or equal to 0. That is, we already know that it's less than 0 from -2 up to 5 halves, not including 5 halves, but it is equal to 0 also at 5 halves. So we would say -2 up to 5 halves, and this time we would put a square bracket on the 5 halves to include it as a place where the function equals 0. And then when is the function greater than or equal to 0? That's going to happen from -infinity up to -2 when it's on the left side of the asymptote. And then also from 5 halves up to infinity, including 5 halves this time. That's if you have the picture. If you have the graph, you can figure these things out fairly simply just by looking. But when you have just the equation, you can't really do that. So we're going to see what we would have to do to solve this inequality. So the first thing we need to do is get everything on one side. So we are going to subtract 3 on both sides. 4x minus 5 over 2x minus 2 minus 3 is less than or equal to 0. Now we need a common denominator, which is x minus 2. So we multiply that 3 by x minus 2 over x minus 2, and then we combine those fractions and simplify it, and we have x plus 1 over x minus 2. There are two significant places we need to pay attention to. We know that the solution set, first of all, is all the x values where the function, that is f of x or y, is negative or 0. That's what we're looking for here, which means below or on the x-axis. It's just a reminder that that's what we're doing when we find the solution set. All right, so there are two issues here for this equation, x plus 1 over x minus 2 equals 0. The function is undefined at x equals 2, so that's where the asymptote is, and it has a 0 at negative 1. That is, it has an x-intercept at negative 1. So it crosses the x-axis at negative 1, and it will change from positive to negative or from negative to positive at that point. So those are two important spots. Everything else we will just look at in terms of these three intervals. We will talk about the interval from negative infinity up to negative 1, the interval from negative 1 to 2, and the interval from 2 to infinity, and we'll see what the numerator and denominator look like in those different intervals. So on the interval from negative infinity to negative 1, we can see, if we try negative 2, we can see that the sign on x plus 1 is going to be negative. The sign on x minus 2 is also going to be negative. And so negative divided by negative is positive. So the sign of the function in that interval is positive. From negative 1 up to 2, in that interval, we can try 0 in each in the numerator and denominator. And when we do that, the sign of x plus 1 will be positive, and the sign of x minus 2 will be negative. So that means that the function itself will be negative because multiplying positive times negative gives you a negative. From 2 to infinity, both the top and the bottom are going to be positive, and so the whole function will be positive. So the only time that this function is less than 0 is when you're going from negative 1 to 2, and it actually equals 0 when you're at negative 1. So your solution set is going to be from negative 1, including negative 1, up to 2, but not including 2 because 2 is an asymptote. First thing we have to do is get everything on one side. So we're going to subtract 1 over x plus 3 on both sides, and then we're going to get a common denominator, which is x minus 2 times x plus 3. And then when we add everything up, we end up with 5 over x minus 2 times x plus 3 is greater than or equal to 0. Now we know that there are two significant issues here. The function is undefined when x is 2 and when x is negative 3. So we are going to have to look at the intervals from negative infinity up to negative 3, from negative 3 to 2, and then from 2 to infinity. So those will be our intervals, and we're going to look at each factor in the function. We've got a 5, we've got an x minus 2, and we've got an x plus 3. 5 obviously is always just 5, so it's always positive. The sign of x minus 2 on the interval from negative infinity to negative 3, it is negative. On the interval from negative 3 to 2, it's still negative, and then from 2 to infinity, it's positive. The sign on x plus 3, when you're in the negative area below negative 3, that is going to be negative, and everywhere else it's going to be positive. So you can see that for the first interval, the function will be positive because it's positive times negative times negative. For the second interval, from negative 3 to 2, we have the negative for the function, and then from 2 to infinity, the function is positive. So the question is, what are the possible values of x where this is greater than or equal to 0, and that's going to happen as you go from negative infinity to negative 3 and from 2 to infinity. So here are some more rational inequalities that we can solve by just inspecting them. We don't even really have to do any work because you can see quickly that this function right here, x squared over x squared plus 4, is always positive or 0. The only time it equals 0 is when x equals 0. And it's always positive other than that because the numerator is something squared, which is always positive. The denominator is something squared plus 4, which is always positive. So this function is always greater than 0 or equal to 0. Doesn't matter what number you put in there. So the solution set for this one is just going to be negative infinity to infinity. For part B, it's always greater than 0 except at that one place where x is equal to 0. So we have to exclude that in this part B because it says only greater than 0. So we're going to say negative infinity to 0 and then union 0 to infinity to show that we're not going to include 0, but everywhere else that thing is positive. On part C, you've got when is it less than or equal to 0? Well, it's never less than 0, but it is equal to 0 when x is 0. So that would be our solution set for that one. And part D, our solution set would be the empty set because this function is never negative. Okay, here is an application of polynomial inequalities. The position of an object moving upward or downward under the influence of gravity is expressed this way. S of t is equal to negative 1/2 gt squared plus b sub 0 t plus s sub 0, where g is the acceleration due to gravity, which you can either say is 32 feet per second squared or 9.8 meters per second squared. T is the time of travel, and v sub 0 is the initial speed. S sub 0 is the initial vertical position. So this is how we talk about falling objects or vertical motion with gravity. And so here's an example. A toy rocket is shot straight upward from the launch pad 1 foot above ground level with an initial speed of 64 feet per second. Write a model to express the vertical position S of t in feet of the rocket t seconds after launch. B, determine the time at which the rocket is above a height of 50 feet. So first thing you're going to do is write the equation. S of t is equal to negative 1/2. We're going to use 32 feet per second squared because we're dealing with feet here, 64 feet per second. So we need to use that one and not the one that is meters per second squared. Then we have t squared plus 64t. 64 is the initial speed, v sub 0, and then 1 foot is where we're going to start above the ground, 1 foot, s sub 0, the initial position. So that's our model, that's our equation. B says determine the time at which the rocket is above a height of 50 feet. So we want to know when is that s of t, that function, greater than 50. So the first thing we need to do is get everything on one side. So we're going to subtract 50 on both sides, and we'll have, after we simplify that and make it look a little bit better, we're going to have negative 16t squared plus 64t minus 49 is greater than 0. So we know that if we use the quadratic formula, we can find out what the zeros of that function are, where it crosses the x-axis. And so you punch all that in, and you end up with negative 64 plus or minus the square root of 960 over negative 32. And then that is 2 plus or minus the square root of 15 over 4. And so that is about 1.03 seconds and 2.97 seconds. And we just need to see when is the function positive, greater than 0, and when is it less than 0 on these three intervals. So from negative infinity up to 1.03, the function s sub 0, we picked 0 to check because it's in that interval, s sub 0 is negative 49. So that interval is not part of our solution. From 1.03 to 2.97, we can test s of 2. We can try 2 because that's in that interval. If we put that into the equation, we get s of 2 is 15, which is greater than 0. So that's definitely an interval where this function is greater than 0. And then from 2.97 up to infinity, if we put in, say, 3 in there, we get s of 3 is negative. So that is not greater than 0. So the only time that this function comes out to be greater than 0 is between the points, the x values 1.03 and 2.97. So what this tells us in this context is that the rocket is above 50 feet between 1.03 seconds and 2.97 seconds after it's launched. And you can see if you graph the parabola that this quadratic equation represents, you can see that that is where the function is above 50 feet, where the y values are above 50, would be between 1.03 and 2.97 seconds.